Hey everyone, welcome to The Explainer. Today we're diving into a question that might make you a little uncomfortable. Why might your medical test actually be lying to you? We're going to explore the hidden math, the messy realities of the laboratory, and the future of diagnostics to figure out exactly why errors happen in medical testing.
Here is our roadmap for today. First up, 1. The scary test result. 2. Math of medical errors. 3. The false positive paradox. 4. Why lab tests fail. 5. The cost of errors. And finally, 6. Fixing the testing process.
Section 1. The scary test result, when panic sets in.
Okay, let's set the scene. It's a scenario we all absolutely dread, right? The phone rings. It's your doctor, and they tell you that a test came back positive. In that exact moment, it feels like a definitive sentence. It feels absolute. Your brain immediately jumps to the absolute worst-case scenarios. But what if that scary positive result is actually just a statistical illusion or a physical lab error? The truth is, medical tests are incredibly useful, but they are definitely not perfect. False positives, when a test detects a condition that isn't actually there, are a very serious and very common concern in the diagnostic world.
To give you a real sense of scale here, let's look at a 2024 study on norovirus testing. Researchers found that a staggering 27.4% of results were potential false positives. I mean, just think about that for a second. More than 1 in 4 positive results in that study were potentially totally wrong. That's a massive, ongoing challenge for healthcare providers who are just trying to get an accurate diagnosis while caring for panicked patients.
And you know, this isn't just an isolated glitch with one specific virus. Take a look at the US rate of false positive mammograms, which reaches up to 15%. Because that rate is so high, over a 10-year period, half of all American women who are screened will receive a false positive. And here's the kicker. 90 to 95% of women who get that positive mammogram do not actually have the condition. Let me repeat that because it's wild. 90 to 95% of these positives are perfectly healthy women. Yet they still have to suffer through the very real, very intense anxiety and distress that comes with that initial phone call.
Section 2. Math of medical errors, the courtroom of science.
To understand why these tests get it wrong, we gotta look at their statistical foundation. And honestly, it operates a whole lot like a courtroom. In statistics, we start with what's called the null hypothesis. Think of this as the medical equivalent of being presumed innocent until proven guilty. In testing, the null hypothesis assumes you don't have the disease. You are presumed healthy right up until the biological data provides convincing evidence otherwise.
So essentially, a test has to make a ruling. It's choosing between two competing ideas. You are either healthy or you are sick. And there are two main ways this ruling can go off the rails. If the test incorrectly rejects the null hypothesis and convicts an innocent, healthy person, that's called a type 1 error. In everyday medicine, we just call this a false positive. On the flip side, if a test acquits a guilty, sick person by failing to reject the null hypothesis, that's a type 2 error or a false negative. As a scientist or a doctor, you almost never get perfect certainty. You usually have to decide which type of error is less dangerous and design the test around that choice.
Section 3. The false positive paradox, probabilities over certainties.
This leads us right into a really fascinating mathematical quirk. Just because a test is highly accurate in a controlled lab doesn't automatically mean your specific test result is the absolute truth. You've probably heard terms like sensitivity and specificity tossed around. Sensitivity is a test's ability to correctly detect a condition when it's really there, and specificity is its ability to correctly identify when a condition is absent. But here's the secret. As a patient, those aren't the numbers you actually care about. What you really care about is the positive predictive value, or PPV. The PPV translates those lab metrics into real life. It tells you the actual probability that you have the disease given that your specific test just came back positive.
Now, that positive predictive value relies heavily on how common the disease is in the first place, what statisticians call the prior probability. The chance of a false positive absolutely skyrockets when a disease is incredibly rare. If you have a test with a fantastic false positive rate of just 1 in 10,000, but only 1 in a million people actually have the disease out in the real world, most of the positives that test finds will be completely false. The test is essentially looking for a needle in a haystack, and sometimes it just grabs a piece of hay that looks a little sharp. This effect is magnified even more in underpowered studies, which makes rare diseases notoriously tricky to diagnose accurately without secondary confirmation. Section 4. Why lab tests fail. The physical reality. Okay, so we've nerded out on the abstract math and the statistical paradoxes, but let's shift gears to the messy physical reality of the laboratory. Because, let's face it, errors aren't just mathematical, they're chemical and physical. So why do tests physically spit out false positives? Well, there are a few usual suspects. First up is cross-contamination. Even microscopic traces of genetic material from somebody else's sample can trigger a positive for you. Then there's cross-reactivity, where your test might detect a totally harmless virus that just happens to be structurally similar to a dangerous pathogen, setting off a false alarm. Add to that things like improper sample collection, degraded samples, expired reagents, or poorly calibrated equipment. And finally, consider PCR testing. PCR tests are incredibly sensitive, which is awesome, but it's a double-edged sword. That extreme sensitivity can easily introduce false positives through overamplification, picking up tiny trace amounts of dead viral fragments that pose literally zero threat to the patient.
Section 5. The cost of errors. When tests hurt.
Look, these math and chemistry slip-ups don't exist in a vacuum. They have severe cascading consequences across all of society. For patients, false positives lead to intense psychological distress, misdiagnoses, and completely unnecessary therapeutic interventions, which, by the way, come with their own physical risks and severe side effects. For hospitals and healthcare networks, it means a gross mismanagement of resources. Valuable time, expensive lab supplies, and limited hospital beds are wasted on redundant follow-up tests, directly delaying care for folks with genuine urgent needs. And on a macro public health level, false positives in infectious disease testing can misdirect resources entirely, leading to totally unnecessary economy-halting quarantines.
If you want to put a tangible dollar amount on just how devastating this can be, look at the COVID-19 pandemic. The data shows that simply improving COVID-19 test specificity to reduce false positives could have saved a single tertiary care medical center up to, wait for it, $202.34 million. Think about that. Just one medical center saving over $200 million in unnecessary hospitalizations and treatments. The financial burden on our global healthcare systems from false positives is truly astronomical.
Section 6. Fixing the testing process. The automated future.
Thankfully, the medical industry isn't just taking this lying down, and the future is actually looking incredibly bright. Laboratories are actively fighting back against these type 1 errors using some pretty advanced technologies and proactive strategies. First, labs are adopting highly specific, validated molecular diagnostic panels. Customizing these panels based precisely on the targeted pathogens greatly reduces the risk of that cross-reactivity we talked about. Second, they're heavily automating workflows. By using robotics to reduce human intervention in sample collection and prep, the chance of operator-induced contamination drops significantly. And third, labs are introducing external quality assurance, or EQA, using synthetic negative controls to continuously catch discrepancies and maintain incredibly strict accuracy standards around the clock.
To see what this looks like right now, you can look at systems like the Biocode MDX3000. It uses the specialized bar-coded magnetic beads technology. It's super cool. It basically lets labs efficiently process up to 96 patient samples in a single run, and they can even run up to 3 different diagnostic panels at the same time. For instance, they can run a gastrointestinal pathogen panel that checks for 17 different pathogens simultaneously from just one sample. This kind of high-throughput multiplex testing keeps hospital efficiency sky high while using advanced molecular design to keep the false positive rate extremely low. It is a massive leap forward in combining speed with precision.
But even as we look at all these incredible sci-fi level advancements, we have to ground ourselves in the core philosophy of science itself. As the scientific literature points out, uncertain results aren't an inherently negative thing. The goal of testing in clinical trials is to reduce uncertainty, not to perfectly eliminate it. Science requires a constant, delicate balancing act between false positives and false negatives. If you somehow create a test that magically eliminates all false positives, you're inevitably going to increase your false negatives, which means sending truly sick people home without the care they need. Reproducibility and validation are the essential safety nets of science, helping us navigate that tricky balance every single day.
So keeping all this math, probability, and laboratory chemistry in mind, here is the big takeaway. Medical tests are powerful, life-saving tools, absolutely, but they are still subject to the laws of statistics. They require context, an understanding of prior probabilities, and a deep respect for type 1 errors. So next time a doctor hands you a positive result, instead of immediately panicking, will you ask them about the false positive rate? Because as we've seen today, sometimes understanding the math is just as important as the medicine itself.